Welcome. In this lesson, we're going to introduce some of the concepts behind graph theory. So graph theory is probably not exactly what you thought it was unless you have actually had an introduction to this before. But let's start off by imagining the following network of friends. Suppose Diana gets a solid case of the flu. So here's Diana. Each vertex or node in the network represents a person. So we have 1, 2, 3, 4, 5 vertices, or you could say you have 5 nodes in this graph, in this network. So each of these nodes represents a person, and each edge between them, so that's this straight line, represents a friendship between the two people it is incident to. So we say that an edge is incident to two nodes or two vertices. Two vertices that are connected are said to be adjacent. So in this is an example of a graph where a graph really is just a structure that consists of nodes and edges. So anywhere there are relationships of some sort, we can represent the entities of that network with vertices or nodes. And we can represent connections between those nodes with edges. So assuming each person only makes contact with one other person during his/her contagious period, is it possible for Diana to spread the flu, ultimately to everyone in the circle? Well, that could be the case, because if we think about it, Diana could make a contact with one of 3 people. So if Diana makes contact with Anne, now Anne gets it, and if Anne gets it, suppose she contacts Elisa, who makes contact with Carl, who makes contact with Bob, and so as a result, that disease will, or that sickness will spread to all of them. And without loss of generality, we could have said Diana gives it to Bob, who gives it to Carl, who gives it to Elisa, who gives it to Anne. So you can imagine that even with with 5 people and each person only making contact with one other person, that disease can still spread. So this is an example of a graph, and by definition, a graph is a finite meaning that it's not infinite, a finite non-empty set of vertices, V, and another set consisting of edges, E. So one of the things that we know is that sets describe many important structures in mathematics, and these sets keep track of the vertices and edges. A complete graph is one in which all vertices are adjacent. So we can think of a graph where we have that. So for example, if we only had 2 vertices, this would be considered a complete graph, because every vertex connects to every other vertex. And if I added a third one, as long as I connected that third vertex to every other vertex, this would be a complete, sometimes we would call this K3, or not K parenthesis 3, but this would be K3. That's the notation we use for a complete graph with 3 vertices. K4 would look kind of like this. We'd have 4 vertices. I'll just draw them as a square, and as long as every vertex connects to every other vertex, then we would have a complete graph. So this would be K4, a complete graph. A graph does not have to be complete. This is just a special type of graph where every vertex, this is the most dense type of graph you can have, where it's the maximum number of edges that you can possibly gain. So in this case, having 1, 2, 3, 4, 5, 6 edges is the most that a graph of 4 vertices can have, provided that we don't do things like have loops or have multiple paths to get to another adjacent vertex. So let's go ahead and take a look at our example. Here we want to describe V and E. What is one way to do this? So one way to do this, and everybody's going to have a slightly different notation. I like to keep it pretty as simple as I possibly can. So if I'm going to describe the set of all vertices in this particular graph, I'm just going to label them A, B, C, D, E for Anne, Bob, Carl, Diana, and Elisa. So those are my vertices. This is a complete listing of all of the vertices in that graph. Now the edges, and I have to be kind of careful here, maybe I should call this, A lot of times the edge set is written kind of more as that symbol. And so the edges, there's a lot of ways we can list these. We can either label all of the edges, but that's kind of redundant because we can specify an edge by describing the two vertices that are incident to that edge. So for example, this edge here would be AB. This edge here would be BC. So maybe I should check them as I go. So that one. Then I have the edge between B and D. I can check that one. By the way, we do not need to list BA, CB, and DB because the network goes both ways. There are other types of graphs that are called directed graphs where there's an actual arrow of flow of information. So there might be situations where Bob shares information with Carl, say on Facebook, but Carl blocks Bob from seeing what he's doing. So we have BD, and then we also have these three edges. So that would be AD, and then here we have AE, and finally we have CE, which is that edge right there, or EC. It doesn't matter which way we list those. So that's a complete description of this graph. Now, there's many ways I could draw this graph, and I'm here my vertices are actual pictures of people, but you see up here, they're just dots, and typically we list them as dots and lines, but this was just a fun interactive example. So this is one example of where we could see graphs, and other examples are the internet, the web. The entire web is a graph where items are documents, and the references, or the links, are connections between those documents. So when you're talking about the World Wide Web, it's a gigantic graph of information. Networks. A network consists of sites that send and receive messages of various types. So you have a site represented by a node, and then you have edges connecting them, or you have links between two sites that represent the edge that connects those two nodes. Program structure. So whenever you're talking about coding, a compiler builds a graph to represent the relationship between classes. The items are classes. Connections are represented by possibility of a method of one class to call a method from another class. So very sophisticated stuff, but the simplicity of a graph. Street networks. So intersections are vertices and edges are roads. Social networks, like the one we saw up here. People are vertices and edges represent friendship. Disease networks. Diseases are vertices and edges are connections between the diseases. So, for example, you might associate certain types of cancer with other types of pre-existing conditions, and having a big graph to represent them would be very valuable. Now, I highly encourage you this will really kind of set the frame, set the mood. This is a really fun, interesting documentary that it's about 45 minutes long. It was put on by BBC. It's called 6 Degrees of Separation. And it actually deals with Kevin Bacon, the actor, who this whole idea of 6 degrees of separation started with, essentially that the distance between any two people in the entire world is no more than 6 people apart, meaning that by having a friend of 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 a friend, I can basically, in that way, relate myself to anyone in the world. Some now argue that 6 degrees of separation is now less due to the internet, and something like more like 4 or 4.3 the last I heard. So some properties and by the way, in this whole lesson, we're just sort of defining things, getting used to terminology, because there is a lot of it. It's a whole new language that we have to learn. So the degree of a vertex is the number of edges incident to that vertex. So and essentially, another way of rephrasing this is how many vertices emanate or originate from the vertex, and you count them, and that's the degree. For example, the degree of Anne is equal to 3 in the example above. So if we look at Anne, we see 1, 2, 3 edges, essentially saying she has 3 friends. Or excuse me, she has 3 friends: Elisa, Diana, and Bob. So here's another example. If we create a small graph, a little sample graph, and we just list these 3 vertices, and we connect them maybe in this way. We call this vertex A, B, and C. We could say that the degree of A is 2 because there's 2 edges coming off vertex A, and vertex B has a degree of Only 1, because there's only one edge coming off of vertex B, and the degree of C is also 1, because there's only one edge coming off of vertex C. Now, there are different types of travel that we can perform on a graph. Whether that actually represents physical motion or not is irrelevant when we're talking about traveling. For example, even in this graph, I could travel from Anne to Carl by way of, say, Diana, Anne to Diana, Diana to Carl. Now, I'm not physically traveling to that person. This is not how far they are spaced apart. This is just an arbitrary sketch of how they are related. So when we talk about travel, it does not have to mean physical travel. Although in the example of streets and intersections, it could mean just that. So there are different types of travels, and the simplest type of travel is a path. And a path is a walk from one vertex to another vertex in the graph. So if I just arbitrarily make up some vertices here, and I'll just label these A, B, C, and D, I can, for example, let me just put one more edge right there. One possible path, and we'll just go ahead and list these out as you can either comma separate them or just list them together. So one possible path would just be AB. Okay, a path is just a walk from one vertex to another vertex. A, B, A would even be another path. Doesn't have any specifications on where it has to start or stop. So A to B, back to A would work. We could go A, B, D, A, C. And we could do A, D, B, D, C, A. Essentially, there are I shouldn't say infinitely many, but yeah, there are infinitely many because we could go A, B, A, B, A, B, A, B all day long. So there are really infinitely many paths that you could take in this network. We want to start placing some restrictions on these paths because a lot of times we don't want to just start and stop at random places. So we have a definition for what's called a circuit. And if you think about like an electrical circuit, a circuit starts at the battery. If you've ever seen a circuit before, it starts at one end of the battery, and then there might be some sort of resistor here or something, and then we close that circuit. So we started here at the battery and we end our wire at the other terminal of the battery, but still at the battery. So a circuit is a path that starts and ends at the same vertex. A path has no restriction. A circuit is a path, meaning that it's just a travel from one vertex to another, but you have to end at the same vertex you started at. So we have to get more specific with circuits for this network up here. So for example, if we started at A, one possible circuit would be A, B, D, A. So notice that our first and last vertices are the same. We could do A, B, A, D, B, A, D, B, A. So we can traverse this graph. We often use the word traverse. A traversal is just a route. We could traverse this graph from clockwise, counterclockwise directions. We could even have other circuits like A, B, D, C, A. We could have A, B, D, B, A. There's just so many circuits, but the restriction is it's a path that starts and ends at the same vertex. Now, we have another type of constraint, and we'll see why these would be valuable, why it's important to talk about cycles and circuits and paths. A cycle is a circuit. So basically, it's a path that starts and ends at the same vertex where all vertices and edges are distinct within that path. So for example, A, B, D, C, A would be a cycle. And if you think about cycle, you just sort of think about the fact that it forms a loop. So A, B, D, C, A. That forms a perfect cycle, right? And then we could go around that cycle over and over again, just like a washing machine or a dishwasher. And we just have to make sure that we don't hit the same vertex twice. So like a possible circuit would be A, B, D, B, A. But this would not be a cycle because we reference or we hit the same vertex twice. And actually, in that case, not only do we hit the same vertex twice, but we also take the same edge more than once. So when we go from A to B, down to D, back up to B, we've basically traversed this edge right here twice, and then when we go back to A, we've traversed that edge twice. And the cycle says it's a circuit where all vertices and edges are distinct within that path. So for this one up here, we could have A, B, D, C, A. That would be one. A, B, D, C, A. So it's a circuit, and it happens to also have the characteristics of a cycle. We could just have A, B, D, A. That would also be a cycle. And we don't have to start at A. That was just an arbitrary choice. We could have done C, D to A to C. C, D, A to C. And so when you're looking at these, you can tell right away that all of the edges and vertices are distinct because we don't ever arrive back at the same vertex again. So that's a cycle. And all of these have their common applications. But before we get into some of those common applications, let's talk about one other way that we could list, or two other ways that we could list the relationships among vertices. So computers need to be able to represent a graph, and they can do it with sets like we've done up here at the top, defining the set of vertices and edges, but there happens to be a more efficient way to do that. And these are a little bit better for computers. For example, we can build what's called an adjacency list. Each vertex in the list is followed by a list of all other vertices it is adjacent to. So we'll just list it in kind of more of a visual form, but we can list the vertex and all of the neighbors of that vertex, or all of the adjacent neighbors of that vertex. So if I list Anne, I see that Anne is adjacent to Bob, Diana, and Elise. So I could list Bob, Diana, Elise. For vertex B, Anne, Diana, and Carl, or Anne, Carl, and Diana, if I want to list them alphabetically, are neighbors. For Carl, Bob, Diana, and Elise are neighbors. For Diana, Anne, Bob, and Carl are neighbors. And for Elisa, we have Anne and Carl as the neighbors. And this is called an adjacency list. If you're wondering if you've ever worked with Python before, one representation of this would be to use what's called a dictionary to record all this information. So you'll often see this as A, like this with a colon, so that's called the key, and the value for that key would be a set of vertices that are adjacent, and we would repeat that for all of the other vertices in this as well. So an adjacency list is something that's usually data structurally a dictionary in something like Python. I think they call them hash maps in Java, but I'm not totally familiar with that, so don't take my word for it. Now, an adjacency matrix is also a way to list relationships. And here's the process. You're going to make a matrix, and you're going to place a 1 in a cell if two vertices are adjacent, place a 0 otherwise, and then we'll answer a question about what other things we can gauge from this. So here's our graph again, and a matrix is going to look like this. So the matrix is just something you might think of as an array in computer programming. And what we do is we just list a row for each of the vertices, and we also list a column for each of the vertices. So you can see that this has 5 rows and 5 edges, therefore it's a 5 by 5 matrix. It'll have 25 entries on the inside. So we're going to place a 1 in the slot if two people are connected. So for example, A and B, Anne and Bob are connected, so we'll list a 1 because there's an edge between them. And also, Bob and Anne, I'll place a 1 here as well because that's the same connection, so there are going to be some redundancies. This would be really handy if you had a directed graph where, let's say Anne shared information with Bob, but Bob did not share information with Anne, and we could have a 1 in one place and a 0 in the other. But we're not dealing with those right now, so here we go. So A to A, well, Anne isn't her own friend, so we list that as a 0. There's no edge connecting Anne back to Anne. And same thing with B to B, with C to C, with D to D, and E to E. So nobody connects to themselves. And then Anne also connects to Diana and Elisa. So Diana and Elisa is a 1, but does not connect to Carl. And notice that this row 0, 1, 0, 1, 1 is the same thing going down for column A, 0, 1, 0, 1, 1, because again, Anne is connected to Diana and Elisa. For Bob, we see Bob is connected to Anne, Carl, and Diana. So Bob is connected to Anne, Carl, and Diana, but not Elisa. And that 1, 0, 1, 1, 0 row will be the same as the 1, 0, 1, 1, 0 column. For Carl, we see that Carl is connected to Bob, Diana, and Elisa. So Carl is connected to Bob, Diana, and Elisa. And same thing for that column for Carl. Diana is connected to Anne, Bob, and Carl. So we already have Anne, Bob, and Carl. Diana is not friends with Elisa, and Diane is not friends with Elisa. So this would be the adjacency matrix. And you can see that this required 25 values to store, right? This requires 25 values that a computer needs to keep track of. This would be handy if you needed to, if you had a very densely populated graph where there were a lot of edges, something close to a complete graph. Because you would want to keep track of all those values. But notice that here, this would be convenient whenever you don't have a lot of neighbors. So rather than have to commit to putting 25 values in memory, which could be a lot more, because typically you have on the order of millions, if not billions, of nodes in real-world situations. So if you're going to have a 1 billion by 1 billion matrix, that is going to be a very large matrix. And if there's not very many edges in it, then it might just make sense to list out the vertices that do have neighbors and to really omit the vertices that don't have any neighbors at all. So how do we decide which to... Oh, and then one other valuable thing here is what is the meaning of the sum of a column or row? Well, if I add 0 plus 1 plus 0 plus 1 plus 1, this tells me that Anne has 3 friends. If I add 1 plus 1 plus 1, that gives me 3 friends for Bob, which is true. Or the number of edges, right? Slash edges. Another way to think about this is that the degree of A is 3 because the sum of row A is 3. Now the sum of column A is going to be 3 as well because it's exactly the same as row A. And so the degree of B is 3. Great, so that gives us some ways of talking about things. Which one do we list? Well, usually an adjacency list is more efficient when the adjacent matrix is sparse. That is, when there are many zeros, meaning that there are not many adjacent vertices. So you may encounter this in certain groups or organizations across the world where maybe the leaders are connected, but everybody's connected to a leader, but not all of the participants of that connection are related to one another. Now, an adjacency matrix is beneficial because mathematics can more readily be performed on it, meaning that we can square a matrix or cube a matrix, and without getting into the mathematics of it, if you were to create this matrix in your calculator, this matrix A, and you were just to raise it to the second power, here's what you would come up with. So here is A squared, and we see that it's not just the square of the elements of the A matrix. Matrix multiplication is a little bit odd. I encourage you to look that up if you're interested. But one thing that we should notice is that the diagonals of the A squared matrix, these guys from top, when we say diagonal of a matrix, we mean from top left to bottom right. Those tell me the number of friends that A, B, C, D, and E have. So the diagonals of A squared tell us how many friends each person has, which is kind of cool. That kind of gives us the sum of the rows as we were summing them up here manually. If you just compute a squared and look at the diagonals, you can see that. And it's totally, and then again, you see the 3, 1, 3, 1, 0 is the first row, 3, 1, 3, 1, 0 is the first column as well, because we're assuming the friendships go both ways. Now, I'll just write this down, and then we can look at it more clearly. But a squared, the off diagonals tell us, a squared tells us how many paths there are between every two vertices via a path of length 2. So what we mean is by way of 2 edges. So for instance, even the diagonals, there are 3 paths from A back to A by traveling across 2 edges. And let's see how that would work. So to get from Ann back to Ann, I could go Ann to Bob to Ann. So because I've traveled from Ann to Bob, I've taken this edge right here. But to get from Bob back to Ann, I've taken a second edge, which is the same one, to get back to Ann. Ann to Diana to Ann is a second way. Ann to Elisa to Ann is a third way. And so in essence, even though it's really telling us how many paths there are between every 2 vertices via a path of length 2, it happens to be for the diagonals that's the number of friends each person has. Now, for example, here, Ann and Bob, there's one way to get from Ann to Bob in a path of length 2. So Ann to Bob, well, there's one direct path, but this tells me that there's one way to get from Ann to Bob in 2 edges. So if you go from Ann to Diana and then to Bob, that's a path of length 2, and that's the only path of length 2, exactly length 2, to get from Ann to Bob. Similarly, if you look at this 3 here, that's the number of paths to get from Ann to Carl by taking 2 edges. So Ann to Carl, here would be 1. Ann to Carl would be Ann to Bob to Carl. Or we could go Ann to Diana and then to Carl. Or we could go Ann to Elisa and then to Carl. And so that's what that tells us. Now you guessed it, a cubed is, the diagonals are not going to really tell you anything in this case, nothing of value. But this tells us how many paths there are between every, so a cubed, and I'll just put, same thing, of length 3. So 3 edges. So there are 2 ways to get from Ann to Carl in a path of length 3. Let's see if we can see that. So I could go Ann to Carl, and we're saying there are 3 paths to get there in a length 3. So we could go Ann, Diana, Bob, Carl. There's 1. Or we could go Ann to Bob to Diana to Carl. That's the second one. Pretty cool. So these matrices are useful for that reason. Now, when we draw graphs, one thing we have to realize is that a graph is fully determined by its vertices and how those vertices are connected to other vertices or incident to other vertices. Adjacent, excuse me. So that begs the question of, if you just gave me a set of vertices and edges, would I necessarily draw you the exact same graph like this? Not really. I mean, with this graph right here, as long as A connects to B, A and B don't have to be left and right of each other. I could grab Bob and move Bob way down here, and just imagine that all those connections are staying the same. I'm just moving where the Bob vertex is, and that graph would still be identical even though it appears different. And we call 2 graphs that are identical based on their vertex and edge set as isomorphic. So basically meaning that they're the same but they're the same change. They're the same morphed graph. Now that seems odd, but let's go ahead and take a look at an example. So if I draw vertex A, vertex B, vertex C, and vertex D over here, and I draw it like this, and maybe I'll put this one here. Let's suppose that what I did is I kept A, B, and C in place, but instead I moved D up here. Well, as long as A and B both connect to D, there's A, B, C, and I've moved D up here, as long as A connects to both D and D connects to B, then I still have this connection from A to C here, and I still have a connection from A to B as well. This graph can be thought of as isomorphic. It's as if we took this and we just sort of, like a rubber band, stretched it out this way and moved it to that point, while preserving all of the links to that vertex. And so these two graphs are considered to be isomorphic, because even though they've been morphed, they are the same. They would have the same vertex and edge set. Okay, so there's a lot of terminology. We're not going to really focus much on this one, but just to be aware, there's something called a multigraph, and it's a graph that allows loops. So a vertex with an edge that loops back to itself. So for example, if I had a vertex that had a loop back to itself, or I had parallel edges like this, then this is called parallel edge, or parallel edges. I know they're not mathematically parallel, but it means they just connect the two vertices in two different ways, and this right here is called a loop. We'll not really focus on multigraphs, but there are some applications of those as well. Now, also, it's important to know whether a graph is connected or not. So it's connected if basically we can somehow get from every vertex to every other vertex. So here's an example of a connected graph. The only way this will be a connected graph is if I could ultimately get from every vertex to every other vertex. Doesn't mean they have to be adjacent. It just means ultimately if I start at B, can I get to C? Well, sure, I can go to A and then to C. If I start at A, I can get to C, I can get to B. If I start at C, I can get to A, I can get to B. And that's called a connected. Now, all I would have to do to make this a disconnected graph is to remove one of the edges. So for example, if I had A and B still being connected, but C is over here all by its lonesome, then this is a not connected graph. And a graph being not connected will affect how we have to design algorithms. For example, if we want to find shortest paths between physical locations on a map, then if there isn't a route to get to another city, then we should basically write that into our algorithm to say ignore any cities that are disconnected from the plan or the map. Here's also a really cool situation. This is an actual graph of the presumed terrorists originally to have associations with 9/11. So you can see that there's a cluster of people, and this is just a small subset of that, but you can see that there are some hubs, and hubs are kind of like points that if you remove them, or vertices, if you remove them, the network would kind of fall apart. And you can kind of see that some of the hubs are the vertices that have the most edges connected. Like if you take off this red vertex, then that deletes a lot of edges. And so any vertex that, if you were to delete it, that takes away a lot of connections is often considered a hub. So Mohammed Abdi is clearly not a hub, because by removing this individual, that network is still a strong network. But if you remove some of these inner points here, you can see that that could break up the communication between the left half and the right half of this particular organization. Okay, almost there. So now we get into some really cool stuff. An Euler path, so a path, remember, is just a path that starts and ends somewhere, is a path in which each edge of the graph is traversed once, perhaps different first and last vertices. So we'll take a look at a couple of examples of this. An Euler circuit is a path in which each edge of the graph is traversed once, but the first and last vertices are the same. So notice it's still using the terminology path in circuit. A path just starts at a vertex and ends at some vertex, whether it's the same one or not doesn't matter, but a circuit has to start and stop at the same vertex. But nowhere did we say that a path or circuit has to go across every edge or traverse every edge in the graph. But an Euler path and an Euler circuit are special types of paths and circuits where we do hit every single edge in the graph exactly once. So let me give you a quick example of that before we look at assess. So like a network like this, a really simple one, A, B, C, and D, if we connected them this way, then we could see that one Euler path, and here we'll also do, there we go. So we made this one a little bit interesting. Let's say I wanted to create an Euler path. So the only restriction is that I have to start at a vertex. I'm just going to pick A, and that I have to take paths all the way around and make sure I hit every edge. So one way to do that would be to go A to E, then E to C, then C to B, let's take that as the third edge, then B to A, that'll be the fourth edge, then let's see, let's say instead we did this. Let's say we took the third edge would be here. Then we'll do D to A. I think I'm going to end up building an Euler circuit here because I'm going to start and stop at the same vertex. But you can imagine that if we, as long as we travel along every edge exactly once, we could start and stop at a different point to create an Euler path. But here we're going to create an Euler circuit. So if we go 1, 2, 3, 4, 5, 6, 7, you see that we start and stop at A and we hit every edge exactly once, meaning not less than once, not more than once. And so our path in this case was A to E to C to D to A to B and then C and then A. Now there's no constraint on the circuit in terms of hitting the same vertex more than once. We can certainly hit the same vertex more than once, but notice that we did not double up on an edge at all. So this is an example of an Euler circuit. And this graph has an Euler circuit. And there's more than one. Of course, we could have gone the opposite way. We could have gone backwards, A, C, B, A, D, C, E, A. And you can find other ones where you go A to B to C to A to D to C to E back to A. And that would be an Euler circuit as well. So these are very useful. Suppose that a city is planning for its new trash program. The goal is for one driver in particular to leave the station, pick up trash along each city street, and do so at minimum cost. Can this be done for the network below, assuming the station is at vertex 1? So imagine that these are street networks, and what we want to do is collect trash along each street. We'll just assume that we're not going to worry about two ways or anything like that. We're just going to worry about making sure the truck goes along each of these edges. And so we want to avoid, one of the things we want to avoid is having to backtrack. We would rather somehow create a circuit, an Euler circuit in particular, to allow us to start at vertex 1 and end at vertex 1. So let's see if this is possible. So for instance, I can go ahead and go from 1 to 0, and then go from 0 to 18, and then 18 to 19, and then maybe I can go from 19 to 5, but wait a minute. Now I can't go back up to 0, because if I do, then I'm going to have to traverse one of the roads I've already traversed. So let me try to take a different path there. And I encourage you to pause and try to do this on your own as well. So here we go down to 5, and then maybe over to 19. But wait a minute. Now if I go up to 18 and back to 0, I'm going to have to go over one of the same edges more than once. So that's going to be kind of inefficient. Let's try a different path. Maybe instead of going that way, I'll just go downwards. And maybe we'll start here and go down there and go along here and along here and maybe here and then here and here. But wait a minute, I'm stuck again. And it seems to be that these top and bottom ones, these ones that have 3 edges coming off them, are causing a problem. So if I start to think about this logically, I have to assess under what circumstances would this be possible. In other words, what must happen for there to be an Euler circuit? Which, by the way, this has no Euler circuit. So in order for something to have an Euler circuit, I need to be able to do 2 important things at each vertex. I need to be able to arrive at a vertex and to be able to leave the vertex an even number of times. In other words, here from 7 to 6, we arrived at 6, and then we left 6. But we have another edge coming into 6, and because we need to collect the garbage on that street, that means I'm going to have to come into 6. But if 6 was not my place of origin, then I would need to leave 6 again, and there's no other way to do that other than to traverse one of the edges that I've already traversed. And therefore, that leads us to the idea that there would be no Euler circuit. Now that holds true regardless of whether you start at such a vertex or not. So we could make the same reasoning above here. If I started at 0 and went to 18, that means I have to leave vertex 0. And then since there are 2 more edges, that means I have to somehow arrive, whether I arrive from this end here, but then I'm going to be forced to leave one more time. And if that was my starting vertex, there's no way to come back to it again. So we see that same issue whether it's the starting vertex or it's just a vertex somewhere in the sequence. We need to be able to arrive and leave an even number of times. So state this as a theorem. So basically, first of all, at every vertex, we need to be able to arrive and leave an even number of times. In order to avoid traversing the same edge twice. So stating this as a theorem, well, what does that mean? If I need to have an even number of arrivals and departures from a vertex, well, if I sum up the number of arrivals and departures, like here I arrived, that's 1. I left, that's 2. I arrived, that's 3. Well, that just happens to be the degree of the vertex, the sum of the number of times you arrive and leave. So we can state it like this. We can say that an Euler circuit exists only if, or if and only if and only if. So this goes both ways. Whether your Euler circuit is the condition and your conclusion is that all vertices have an even degree, or if you know that your graph has all vertices with an even degree, then you know an Euler circuit exists. So if and only if the degree of a vertex V is even, or I'll write it like this, V sub I, V with the subscript of I, is even for all I. That is, for all vertices. Nice. So as long as you count the degree of all vertices, and if you're using a computer and you're trying to find whether a graph has an Euler circuit or not, then an adjacency list is fantastic. Or using the adjacency matrix, you can just make sure that the diagonals for A squared are all even. Like this one, I can tell right away that this graph is not going to have an Euler circuit. There's no way I could start at n and get back to n by taking every edge once, because I'll have to leave n and then arrive back at n and leave n again, but then I can't get back a 4th time. So that's pretty cool. That's what we use Euler circuits for. There's an example where you want to build an efficient network. Now, just because it doesn't have an Euler circuit doesn't mean that all is lost. It just means that the route is going to have to come back along one of the streets. So it's not the end of the world, but looking for Euler circuits is nice because then that tells us that that's the most efficient route we can take. Okay, suppose the city needs to do maintenance on the streetlights in the above network. Does there exist a way to start at the station and to visit every intersection exactly once and back up at the station, thereby minimizing redundancy? So assume all intersections are equally spaced. Okay, so in this case, we want to do maintenance on the streetlights. And so if we start at, say, vertex 1, we want to hit every vertex exactly once. So I can go from, for example, 1 to 4, 4 to 7, 7 to 6, 6 to 20, 20 to 19, 19 to 18, 18 to 0. But I need to start and stop at the same vertex in order to minimize redundancy. I don't want to have to go along one of the same intersections. Like if I went this way, well, clearly at this point now I'm going to have to visit a vertex I've already been at to get back to my starting point. So there is some redundancy. And the process of being able to start and stop at a vertex, visiting every vertex exactly once, is what's known as a Hamiltonian cycle. So it's a cycle that includes each vertex of the graph. In general, it is harder to determine one, and the theorem for existence of one is rather tedious. So we don't focus a whole lot on Hamiltonian cycles. Some graphs have them, so I could draw you a graph that does have a Hamiltonian cycle where, like right in the middle, let's say we have A, B, C, and D, like this, and we have maybe a connection there, and we have a connection here, and like this, and maybe we also have a connection there. So one possible Hamiltonian cycle would be to go from A to B, visit C, visit D, come back to A. We didn't hit every single edge, but that's not what a cycle requires. So this has a Hamiltonian cycle. Now there are some theorems that allow you to determine whether one exists. And here is one, and we're not really going to use it because it's really inefficient. Suppose G is the name of a graph with n vertices, where n is at least 2. If for each pair of non-adjacent vertices u and v, we can add together their degrees and it's at least the size of n, then G has a Hamiltonian cycle. So what we mean by this theorem is if we compare every vertex to every other vertex that is not directly connected to it, like this, in this graph. For instance, this does have a cycle because I can see I can just go around this shape. But if I looked at this theorem, this would say that I have to sum the degrees of vertices that are non-adjacent. So for example, A and B are adjacent, A and D are adjacent, so I can only look at A and C. And the degree of A plus the degree of C, well, A has degree 2, C has degree 2, it's equal to 4, which is in fact greater than or equal to the number of vertices we have in this graph. We have 4 vertices in this graph, and so we've satisfied that condition. We would have to do the same thing for vertex B. B is only non-adjacent to D, and if we add together the degree of B plus the degree of D, we also get 4, which is in fact greater than or equal to the number of vertices in the graph. And the same thing would hold for vertex C, because C and A would be paired, B and D would be paired. So since the sum of these degrees is greater than or equal to the number of vertices in this graph, this definitely does have a Hamiltonian cycle. You can imagine that this can become very tedious if you have hundreds or thousands of vertices in your graph. Given you have to check every pair of non-adjacent vertices, this theorem may be harder to apply than to conduct a brute force search for a Hamiltonian cycle within a graph. So there are algorithms out there that will help us find these, and just because this theorem is not satisfied, even if it doesn't pass, doesn't mean that the graph doesn't have a Hamiltonian cycle. It just means that if this condition is satisfied, then it does have a Hamiltonian cycle. If this isn't satisfied, we just don't know. And we'll go ahead and stop there. So in the future video, we'll actually get into some features of graphs and how to perform some algorithms on those graphs. So see you then.